Hi everyone, I'm Georgiana Esquivias, the Senior Project Analyst for ImageCat, and today I will be discussing the methods of mapping financial exposure. First, I will explain how the Building Exposure Database is developed and then follow up with our critical infrastructure indices. The basic process for developing a building exposure database consists of gathering numerous data sets and information regarding these 5 primary elements, which I will go through briefly. Using the population and building attribute data from census and housing reports, an engineer can begin to develop a mapping scheme that characterizes the typical construction type patterns, which we name development patterns, for any given country. The detail in the mapping scheme will depend on the spatial resolution of the available data, and this information can be used to extrapolate or infer building counts, building area, and construction types. In this Nepalese example, our engineers were able to make a direct correlation between the number of stories and structural types. Earth observation data is used to estimate the number of buildings in building area through an automated building footprint extraction. Combined with a stratified sampling strategy, we're able to make a correlation between the built area and household sizes. Replacement cost values are gleaned from various building construction manuals and estimated using the calculated building areas. Now, disametric mapping is a very intricate process that involves using Earth observation data as weights to train a regression model. These models establish the distribution statistics for reallocating the number of people and buildings from an administrative unit area to a more refined grid cell based on observed urban density and development pattern types. Modeling using Earth observation data and various machine learning algorithms allows us to further increase the segmentation of development patterns by construction types. This process plays a key role in identifying critical infrastructures and industrial assets that are vulnerable to natural disasters. In the images above, we can see how the industrial zones are detected by the machine learning algorithm. We aggregate the high-resolution results to a lower resolution grid cell in order to minimize the noise in the analysis and provide a more realistic development pattern designation. Now, applying the building exposure development methodology, we can detect regions of production. Then, when overlaid with global hazards or vulnerability datasets, we can identify localized indicators of risk. As well, when the critical infrastructure zones are fed into a regional economic model, we identify where these localized losses may trigger a cascading economic event. Here are a few examples of our Critical Infrastructure Interdependency Index and Risk Rank product. The Critical Infrastructure Interdependency Index measures how much international and domestic economic activities depend on a specific region's production output to produce other goods. This index provides a synthetic indication of the interdependencies within and across domestic and international supply chains, and allows for the comparison between regions in terms of their contribution and role to the global supply chain. This is independent of how prone these regions are to hazards. Then we take the interdependency index and combine it with local hazards to obtain a risk rank. The Critical Infrastructure Interdependency Risk Index combines the notion of the interdependency index with local hazards. Hazard is incorporated through a probabilistic approach, while the vulnerability is embedded in damage functions. The Critical Infrastructure Interdependency Risk Index allows us to compare or rank different regions according to their risk to supply chain disruption. It also highlights regions where more in-depth analysis are required. This concludes my presentation. I hope that you have found this information useful, and feel free to contact me if you have any questions.